the real number system. Now, you might be thinking, well, why do we call them real numbers? And you either think that because, like, all numbers must be real, or you think numbers aren't real, they're just a thing we use to describe things. Well, you don't have to know this at this level of your education, but there's actually something called imaginary numbers. And I'm not going to go into why they're called that, but I'll just tell you they're actually super helpful for things like magnetism and electricity when they're trying to help run circuits and figure out volts and hertz and all those kind of things. But we just deal with the real number system. And the real number system encompasses everything you see here. So these are all in the real number system. So the real number system actually covers everything we see here. So all of these in here are part of the real number system. And we can essentially divide the real number system into two sections. Now, I don't mean they're equal. The point is not the size of them. But it's almost like you could then separate the real number system into rational numbers and irrational numbers. So rational numbers are numbers that can be written as a fraction. Now, that doesn't mean they are written as a fraction. Some can be decimals, some can be whole numbers, but they can be written as a fraction. So let me go ahead and fill in this blank, and we'll come back to this picture, because I think this picture is very helpful if I can help you understand it. So rational numbers are numbers that can be written as a fraction, but they can be written as whole numbers or decimals as well. So just to illustrate a little, and on the back we're going to do a lot of working with these, but just to kind of give a picture of what we're talking about right now. So obviously rational numbers would be things like 1/2, -4/5, 7/3, any fraction you can think of like that. Those are rational numbers. Rational, the word, actually implies a ratio, which is a fraction. But whole numbers, all whole numbers are also rational, because you can take any whole number and make it a fraction just by putting it over 1. So any whole number, I should say integer, but we haven't gotten there yet. What you think of as any whole number can be made a fraction just by putting it over 1. Now, plenty of decimals can be written as fractions. Any decimal that ends, such as 0.3, it can be written as 3/10. Or 0.25 can be written as 1/4. Or ones that repeat, and that keeps going forever, also can be written as fractions. This one in particular is equal to 1/9. Now, you don't have to have all these memorized at the moment. It's nothing like that. But just what you need to understand is rational numbers are either fractions, they're whole numbers that we can write as fractions, which is all whole numbers, or decimals are rational numbers if they're decimals that either end, so that's an example like 0.3, 0.25, and it may have a lot more decimals. I mean, we're not going to typically deal with this, but it could be like 0.754318. But if it actually stops there, it could be written as a fraction. It'd be a crazy one, but still, it can be written as a fraction. Or if they have a repeating pattern. So that was why I showed you this example right here. So 0.1 repeating is still a rational number because it can be written as a fraction. Or another one would be 0.16 repeating, which you can also write this way. I think we've talked about this before. This little hat or this overhead line, that means the 6, and only the 6 repeats. So this is actually 1/6. So 1/6 is equal to this. So anytime they end or they have a repeating pattern, it is a rational number. Okay, so irrational numbers, we'll talk about these three subsets in a minute. But like I said, the real number system, that's the whole thing. Then we split it up into two sections: rational numbers, which we've talked about, and irrational numbers. So irrational numbers, I know this is shocking. Rational numbers are numbers that can be written as a fraction. Irrational numbers are numbers that cannot be written as a fraction. Now, we don't interact with these a whole lot. but let's just fill in the blanks down here, and I'll talk more about it as we do. So the number pi is a famous example. Now you might know 3.14, and some of you may know a few more digits like 159. But I think they've studied and figured out pi out to like millions of decimal places, but it never ends, and there's no repeating pattern that they can detect. So pi is an example of something we cannot write as a fraction. Now we can estimate it. I think 22/7 might be something you learned at some point in elementary school or earlier in middle school. But that's not exactly pi. That's just an estimate of pi. Just like when we use 3.14, that's just an estimate. It's a rounding off. So irrational numbers are decimals that have no repeating pattern and never end. So the main ones that we're going to see are pi. So I'll just write this up here. Pi. And if we look at what it says in this last section, all square roots of whole numbers that are not perfect squares, which we talked about previously, are irrational numbers. So let me give a comparison here. So rational, square root of 4. That's rational because that's equal to 2, and we can make that a fraction. Square root of 81, that is a perfect square. It's equal to 9. We can make that a fraction. But the square root of 2, we can't take the square root of that and get a whole number. It's not a perfect square, so it's irrational. Same for square root of 3, square root of 11, square root of 12, square root of 24, and you could keep on going. Now, we've talked a little about, I think we have. If we haven't, that's okay. Sorry, I've been making lots of videos and I get confused sometimes. But if you know what prime numbers are, it's not just prime numbers inside that make irrational. It's any number. Like 12 is not prime. There's lots of numbers that go into 12 other than 12 and 1. Same with 24. So it's not an issue of prime versus composite. And if you don't know those words, that's okay. That's not the point. The point is, it's only perfect squares that square roots turn rational. Any other number other than those perfect squares, when you take the square root of it, it's irrational. Now, these aren't the only irrational numbers in all of math, but as far as what we're going to see, this is typically the two things you'll find. Pi, or a square root that's not of a perfect square. So again, let's back up. The whole big system is called the real number system. That splits into two pieces, the rational numbers and the irrational numbers. Now, inside the rational numbers, there's three more groups. So they put these blocks here to help you understand that inside the rational numbers, there are integers. So integers are any whole number that's positive or negative or 0. So that includes, often when we say whole numbers, mathematically that doesn't include negative numbers, but we mean it to. But officially, integers are anything that can be written as a whole number as positive, negative, or 0. Then inside that, basically we cut it off and say, okay, let's nix out the negatives and not include them. So if we only include 0, 1, 2, 3, and on, those are what are officially called whole numbers in math. So we often unofficially mean, it can be written not as a fraction or a decimal. We call it a whole number. But officially, a whole number is 0 in all the positives that are whole. Integers is 0, all the positives, and all the negatives that are whole. And then what's frankly kind of a silly little things they say, what if we make a group that just takes out the 0? It only includes 1, 2, 3, and beyond. So that's called natural numbers. These can sometimes be called counting numbers, just because when you first learned numbers, you learned to count 1, 2, 3, 4, 5. So the only difference between these two, natural and whole, is whole has a 0. So if you just remember, whole has 0. That can help. So you can also think about it from small to big. So natural numbers are the numbers we learn to count with. Whole numbers are the numbers we learn to count with and 0. Integers are all the numbers we learn to count with, 0, and the negative version of the whole numbers we learn to count with. And then rational numbers includes everything that we can't turn into a whole number, an integer, that's a fraction or a decimal, but it has to be a decimal you could write as a fraction. So I mean, the things that are in this category could be things like 1/2, 0.3 repeating, anything like that. So let's flip to the back. So we want to name all the number sets to which each real number belongs. So first, we want to see if we can reduce this at all. And we can. 21 over 7. 21 divided by 7 is 3. Okay, so let's look back here. 3, well, that's included in the natural numbers. And if it's in the natural numbers, it's in all of these as well. Because all natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. And all rational numbers are real. So anything in this category includes all 5 of these labels. So I know it's a lot to write, but 3 is natural, falls in that category. And this is why it says name all. So you can't just say natural, you have to say natural, whole, integers, rational, and real. Okay, negative 2.5. So that can't be written as a whole number. It's negative, but like negative 2 is an integer, negative 3 is an integer, but this is not even a negative version of a whole number. So that means it's not a natural number, it's not a whole number, it's not an integer, but it is rational. It is rational because we could make that a fraction. We could make that negative 5 over 2. Now, you don't have to write the fraction for me. I'm just trying to show you how this is rational. You could also just remember that since this is a decimal that ends, that means it is rational. So all we have to write for this one is rational and real. Okay, C, we have 0.2 repeating. Just, I could write it this way, or I could say 0.2 and then this bar above it, and that means 0.2 repeating. So these two mean the same thing. So this does not end, but it has a repeating pattern. It's 2 every single time, all the way forever. So since it's a decimal with a repeating pattern, that means it is rational. It can be written as a fraction. In fact, this is 2/9. And if it's rational, it's also real. Okay, this is the square root of 38. 38 is not a perfect square. The square root of 38 is not a whole number. That means we cannot write this as a fraction, and that means it's irrational. But rational and irrational numbers both fall under the real category. So all the numbers I provide for you are going to be real. But then it's just a question of, is it in the irrational or rational category? And if it's rational, does it fall in any of these as well? Okay, so for the following two problems, express each number as a decimal, then compare them. So you can use your calculator to do this. So in your calculator for 3 1/3, you could do 1 divided by 3, hit enter, then do plus 3. You might be able to do it all at one time because it'll follow the order of operations, I think. You could also do it 3 plus 1 divided by 3. 1 divided by 3. If you do it all in one line, it should follow the order of operations. But this will be 3.3 repeating. And then you do the square root of 15. Let me pull up my calculator. Actually, I think I've got it over here. Oh, I do. So never mind. I'll just use my key. Haha, cheating. So 3.873. Now I just picked the first 3 decimal places. It goes on forever. Really, you just need to do enough of them to be able to tell clearly which one is bigger or smaller. Well, this one's 3.3. This one's 3.8. So 3.3 is clearly smaller than or less than this. And the main point that they're trying to show here is it's often hard to figure out which number is bigger or smaller when we're in different forms. And we can't change everything to a fraction because irrational numbers won't change to a fraction. But we can change everything to a decimal. So that's often the best thing to do so that we can compare the size of 2 numbers. So 7 2/5. So 2/5 is 0.4. So this is 7.4. The square root of 57 is 7.55. Well, 7.4 is less than 7.55. So 7 2/5 is less than the square root of 57. Now they gave us 4 numbers. They want us to order them from least to greatest. So let's convert all of them to decimals. 8 4/5, you can do 4 divided by 5 in your calculator. That's 0.8. 8 plus 0.8 is 8.8. You should know this one by now. The square root of 64 is 8. This one's already a decimal. And then you can type the square root of 76 in your calculator. It's 8.72. Okay. Now, when we list these, we need to list them in our final answer just the way they're written right here. But honestly, it's easier at this point to go ahead and just put them in order in decimal, then we can convert them back. In other words, I'm going to go ahead and say, okay, from least to greatest, 8's the smallest, and that's the square root of 64. The next smallest would be 8.3 repeating, and that's just written just the way it is. Next smallest would be 8.72, and that's the square root of 76. The biggest is 8.8, which is the same as 8 4/5. Now, if you don't need to write this line to figure out this line, that's fine. I trust you. You just need to, I just want to show you that if it helps you to put them in order in decimal form first, then you can just convert them back. That's why I wrote their equivalent directly under them, so I knew which went with which. So this would be our answer. We're putting those in order from least to greatest. Okay, last type of problem we need to know with these, and that's how to solve an equation that has a squared in it. So to do that, we have to do the inverse. So for example, let's think down here. We know this is 2 times n squared, so we know the first step we take here is to divide by 2. And the reason we do that is we're always going to do the inverse of what's happening to the variable. The variable is being multiplied by 2, so we need to divide both sides by 2. So in a similar way, the variable is being squared, so we need to do the opposite to it and take the square root of both sides. So the square root of a squared is a, and I'm leaving some space here on purpose, so just watch me before I write it down. The square root of 36 is 6. However, anytime we have to take the square root to solve for a decimal, we have to put plus or minus in front of it. So again, when we're solving for a variable, I may have said decimal, sorry. When we're solving for a variable, we have to put plus or minus in front of our answer. And here's why. We know whatever a is. When we square it, we get positive 36. Well, if I plug in 6 and square it, that gives me 36. When I plug in negative 6 and square it, negative 6 times negative 6 is also positive 36. So we have no way of knowing if a was originally positive 6 or negative 6, because both of those will give us the same result. So we have to put that a is equal to plus or minus 6. We're saying it could be either one. We don't know which. So now back to b. Like I said, we needed to take care of the 2 first. So 2 was being multiplied, so we divided both sides by 2. Then we'll take the square root of both sides to get rid of the squared. The square root of n squared is n, and because I'm solving for a variable, and I took the square root, I have to put plus or minus. And notice it says round to the nearest tenth, so we don't have to try to simplify or anything like that. We can just type square root of 85 in the calculator, and rounding to the nearest tenth, you'll get 9.2. So the answer is plus or minus 9.2. Okay, on this one, similar pattern. Doesn't matter if the variable's on the left or the right. We divide both sides by 3. We get 121 equals d squared. Then we take the square root of both sides. The square root of 121 is 11, but because I took the square root of a variable and I'm solving for a variable, I have to say plus or minus 11 is equal to d. And if it'd make you feel better to put the d over here and say d equals plus or minus 11, that's fine. Both forms of that are good and equally correct.